So in this example, we're told that we have a piece of sheet metal which is 60 centimeters by 30 centimeters, and it's to be used to make a rectangular box with an open top. Find the dimensions that give the box with the largest volume. So when they ask you a question like this, they mean for you to make the box in a very, very specific way. Let's just draw out what our piece of sheet metal looks like here. It's a big rectangle. We've got 60 centimeters by 30 centimeters. Okay. To make this into a box with an open top, they want you to cut out a square from each corner. And all of these squares will be exactly the same size. Once you've cut out these squares, we've got these little flaps here and here, here, and here. These flaps are going to be folded up and then joined together, and those flaps are going to form the sides of the box. Okay? So this dotted rectangle in the middle is going to be the base of our rectangle, and these four things around the sides are going to be the sides. Side, 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 and side. So that's our situation here. Now, what are we trying to optimize in this question? What are we trying to make as big or as small as possible? Right. The volume. So we need an expression for the volume of our box. Now, volume of a rectangular prism, just length times width times height. Okay. So we've got three variables here that we're going to be working with. Well, and we want to get rid of two of them because we always want this to be a function of a single variable. So going back to our diagram, if we're thinking about our final box, the length of our box is going to be sort of the length of the base along here, okay, from here to here. The width of our box is going to be the width of the base along here. Okay. What is the height of the box going to be given by? The width of the side, yeah. So this little thing in here. So what determines the height of the box is how big this square is that you cut out from each of the corners. You cut out a bigger square, and you're making the height of your box bigger. If you cut out a smaller square, you're making the height of the box a little bit smaller. So what we need now are we need relationships between length and width and height. Okay? And height is the variable that we want to work with here. So we want to express our length and our width in terms of our height. So let's see if we can do that up here. How can we get a relationship for our length and our, let's start with the length. Length in terms of our height here. Well, the length that we start with for our piece of sheet metal is 60 centimeters. We're cutting it down by taking away a chunk of size h from either side of it. So our length is going to be what we're left with after cutting out h from this side and h from this side. So the length is going to be 60 minus 2h. Okay? So that's the red length there on the inside of our, that is the base of our final box. Okay? Similarly, the width of our box we get from taking the overall width of our starting sheet and taking h off from one side and h off from the other side. So that's going to be 30 minus 2h. And there's our expressions for length and width in terms of our height. Now, Are there any restrictions that we can place on this variable that we're working with, h? The easiest one is that h has got to be greater than 0 because we can't have a negative height to our box. What is the largest possible value that h could have here, Malcolm?
15.
Why 15?
Smallest number is 30.
Mm-hmm.
And there has to be at least 2h.
Yep. Yep. So if we take 2 times 15 off of w here, 30 minus 2 times 15 would give us a width of 0. And once we have a width of 0 or a length of 0, we no longer have a box. We've got a, I don't know what we have anymore. Again, just a flat sheet or something like that. Okay? So we've got the quantity to be optimized, volume. Now we can express it in terms of one variable. So we can sub those expressions for length, 60 minus 2h, width, 30 minus 2h, into that function for volume. So now we have a function of a single variable. So we can go ahead, we can take our derivative, set it equal to 0, and solve for critical numbers. How would you take the derivative here? Well, if you wanted to, you could try using the product rule, but you would have to use the product rule twice. I think it's easier in these cases just to expand and simplify. So I'm going to expand out those two binomials there to get 1800 minus 120h minus 60h plus 4h squared. Multiply that whole thing by h. I can collect those like terms in the middle and multiply everything by h to get 1800h minus 180h squared plus 4h cubed. Still volume. Now we're ready to take our derivative. So the derivative of our volume function with respect to h is going to be 1800 minus 360h plus 12h squared. And this we want to set equal to 0. Okay. Well, let's see. We can divide everything through by 12, and that 12 is just going to go away because we've got 0 on the other side, which is going to leave us with h squared minus 30h plus 150 equals 0. Ideally, we would solve this by factoring. I don't think this is going to factor, so we're going to have to use the quadratic formula. Quickly doing the quadratic formula gives us two solutions, 23.66 and 6.34. Which of these solutions are we going to use here? Liam?
6.34 because it's in the domain.
Yeah, only one of these is in our domain, so we can immediately get rid of that one right there. So our answer for h is 6.34. Now, let's double check, make sure that this actually corresponds to a maximum value. We'll use the second derivative test here. So our second derivative is minus 360 plus 24h. So we want to evaluate this at 6.34. So we'll say v double primed at 6.34 equals negative 360 plus 24 times 6.34. And we could just punch this into our calculator, and we get something like negative 207.84, whatever. Now remember, we don't really care about what the exact value is for our second derivative. We really just care about whether it is positive or negative. If the second derivative is negative, then again we have a local max. which is what we were looking for. We're looking for the maximum value of our volume. So we're good. A height of 6.34 centimeters gives us our maximum volume. So let's go back to the original question here. It asks us for the dimensions of the box. So we have the height. We need to also find our length and our width. So of course we're going to use these two relationships that we got back at the beginning for length and width in terms of height. So 60 minus 2 times h and 30 minus 2 times h. So let's work out what the length and the width are here. We punching this into our calculator, we get 47.32 for our length and 17.32 for our width. So the box should be, let's see, 6.34 centimeters by 17.32 centimeters by 47.32 centimeters.